So we've done a lot of work on gravity, and now we're going to formalize it mathematically with the idea of a gravitational field. So this is a new word that you've come across. If you're into science fiction, you've seen a lot of force fields being used. The idea of a field is that depending on where you're standing, there is a particular direction you're going to go. So the way you calculate a field for force is you take the equation for that force. So for gravity, it's gm over r squared. And you identify the thing that is causing the field and the thing that is affected by the field. So in this particular example, suppose I wanted to know where this particular mass was going to move to because of the other two that are up there. So if I wanted to know that, then it's these two objects that are causing the field, and then this is the one that's experiencing it. So in this equation then, I would end up with this piece being the thing affected by the field. And then the gmr squared are the pieces that are causing the field, or at least causing the number part. So if I take it and I divorce it like that, I end up with F equals gm over r squared multiplied by the test particle. So the thing that's being affected by that particular object. Now this is starting to look a little familiar, right? F equals mass times something. Well, it looks like this is just acceleration. The acceleration caused by the net gravity of everything around there. So that's sort of what the definition of a force field is. Field is the acceleration map, if you will. For an object that is experiencing forces. This marker is almost toast, I think. Okay, so if we were really skilled at algebra, what we would do is not fill in any numbers. We would leave this expression as a set of variables. And then you could plunk those variables into a computer and the computer would run a simulation for you. What we're going to do is just calculate the field strength at a particular spot. Now that sounds maybe a bit daunting, but you've been doing this the entire time. You notice that when we did the force calculations right at the gate and the energy calculations right at the gate, I left this number undefined. I said, well, whatever, we'll fill in your mass or the ship's mass or whatever's mass later. I just want to worry about this, and we'll quote all our answers in newtons per kilogram or joules per kilogram. Well, what you were doing was you were calculating an acceleration field or a force field based on the energy or the force equation by leaving that test mass undefined for a moment. So if I were to do this in terms of gravity, right, the thing that we were doing on Earth looked like this, mg, and g was calculated by doing this thing. In order for force to be a vector, right, to have a direction, one of these two things has to have a direction. And mass doesn't have direction, but g does. On Earth, it's down. In this particular example, it will be somewhere like that, right? Attracted to that one, and passing somewhere between them. So when we're trying to calculate gravitational field, it's this thing that I'm after, right? Calculated by gm over r squared for each object that is contributing to the field of that location. that was a lot of words. So we're going to just do one. You'll see that it's not quite as scary as it seems. So let me erase this. Okay, so question 1. Where will this guy go? So the first thing I'm going to do is I'm going to eliminate this person entirely, because their own gravity is not going to cause them to accelerate. Their own gravity would cause them to stay where they are. So I'm just going to make this a space holder for the object I just took away. I have a triangle here with some angles, like I know 3 sides, so I could use cosine law to work out some of these angles. Set them up like that. So cosine law is c squared equals a squared plus b squared minus 2ab cos of the angle in between a and b, so that's here. So c squared is opposite, that's 4 times 10 to the 7. A would be this side, let's say, 3 squared. This side squared. I'm dropping the 10 to the 7s because they're all 10 to the 7, so my answer is just going to be 10 to the 7. I can save myself some heartache. Minus 3 times 2 cosine omega. 4 squared is 16. Subtract 9. Subtract 4. 3 times 2 is 6. 16 minus 9 is 7. 7 minus 4 is 3. So 3 over negative 6 equals cos omega. So omega then will be the arc cos of negative 1/2. Okay, now 1/2 is a special triangle. So let's see, did that work out right? 4 squared, 2 squared, 2 squared. 6, 9, 4 is 13, 3 divided by 6, yep, it's all good. Okay. Alright, so on the 1, 2, root 3 triangle, pi over 3 goes here, sorry, got calculus on the brain. 60 degrees goes there, 30 degrees goes there. And if I'm trying to get a cosine of adjacent over hypotenuse, that's going to be 60. So this is in the 60-degree family. Cast rule says that I get cosine values that are negative in this quadrant and this quadrant. So in order for it to be negative 1/2, I'm going to end up with omega being 180 minus 60 is 120 degrees, or omega equals, the one down here would be 180 plus 60, which would be 240. And we all know that you cannot have more than 180 degrees in a triangle, so that one is right out. Okay, so this angle here then is 120 degrees. Lovely. So I'm going to figure out these other angles then. I'm going to go after this one next. I'm going to erase some of my board here. So I'm going to use sine law. So sine of alpha over 3 times 10 to the 7 would equal sine 120 over 4 times 10 to the 7. You can see how the 4 times 10 to the 10 to the 7s aren't going to matter. Sine alpha equals 3 times 10 to the 7 sine 120 over 4 times 10 to the 7, and then those divide out. So I need to take the arc sine of, let's see, 3 times sine of 120 divided by 4 gives me 0.6495. And if I arc sine that, get 40.5 degrees. When you arc sine, you get two answers. The other one, of course, is the one up in this quadrant, which is 139.5. But I've already used up 120 degrees, so there isn't enough left. 120 and 130 would be 250. That's too much. So I can discard that option. So this angle up here is 40.5. Angles in a triangle have to add up to 180, and so far I've used up 160.5. That leaves 19.5 degrees. Just check that. 19 and a half would be 20, 20 and 40 would be 60, 60 and 120 is 180. There we go. So I can clear this stuff off, and then just to make sure that my components are easy to manage, by Z pattern, this is also 40.5 degrees, and this is also 19.5 degrees. Okay. So if you're standing at that spot, there are two pieces to the gravitational field. There's one that is attracting you towards this object up here. There is a second one that is attracting you up to that object up there. And the net gravitational field will be the two of those things added together. But since they point in different directions, I have to add them like vectors. So I'm going to have this in an x and a y coordinate, and then add them that way. So I'm going to have to set up some triangles and break those two forces up into components. So the blue one. Blue. As if you couldn't tell that was blue. The force pulling me that way, the force of gravity, is Gm over r squared. But this is why we're going to use field. Instead of saying the force of gravity, I'm going to use the gravitational field. And that allows me to just dump this m, and then I don't have to worry about it. So little g with an arrow on top for gravitational field. If I work that out, g is 6.67 times 10 to the negative 11. And the mass attracting me is 6 times 10 to the 24. And my distance from there is 3 times 10 to the 7 squared. So 6.67 times 10 to the negative 11 times 6 times 10 to the 24 divided by 3 times 10 to the 7 squared gives me 0.4446667. So I'm going to round that to 0.445. Right. Lovely. That's how strong it's pulling, but it does not give me anything about the direction. What I can tell from this is that this side is adjacent to the 19.5 degree angle. So that's a cosine. So what I'm going to attach on the back of here then is cosine 19.5. Because if I were to try and do this with a triangle, I'd have this number multiplied by that, and then this multiplied by the sine of the angle. So I'm just going to leave it as a separate object. I am going to note that this is going to the left, so this needs to be negative. This component, the vertical one, will be adjacent or opposite over hypotenuse, so that will be sine of 19.5. And it is headed up, so I'm going to leave that as positive. So this vector then is 0.445 negative cos 19.5 sine 19.5. Okay, so you notice that this thing was not in the formula I had originally. This thing is called the direction vector. It has a length of 1. You could try it. Square this, add them together, you're going to get 1. That is in fact one of your trigonometric identities from advanced functions in grade 11 math, that cos squared plus sine squared equals 1. So it's got a length of 1, so it's not going to muck this up when you multiply them, but it does happen to point in the direction I want. So the vector that points in the direction I want is called r hat. That's what this is. So this is my answer then, and it's been given in gravitational field equals the size of the gravitational field multiplied by the direction of the field format. So when you see the question ask you for something like in this format, that's what I want you to leave it as. Don't bother doing the multiplications. Don't even bother multiplying or applying the cosine or the sines. It just makes messy decimals that we don't really need. Okay, so there is my work for the blue vector. I'm going to need to do the same thing for the pink one. Why don't you just do the marker in pink and blue, they ask. Well, because they're kind of hard to read, so I'll stick to green and yellow. For the pink one, if I want the gravitational field, I need g m over r squared, and then r hat, the direction I'm pointed in. So for this pink one here, g is still 6.67 times 10 to the negative 11. The mass attracting me is 2 times 10 to the 24. And this time I am 2 times 10 to the 7 away, instead of 3 times 10 to the 7. And my r hat, the vector that's going to give me the direction, the horizontal is adjacent to the 40.5, so that's cosine. And the vertical is opposite, so that's sine. It's headed to the right, so that should be positive. It's headed up, so that should be positive, so I'm going to leave it like that. My gravitational field then will be 6.67 times 10 to the negative 11 multiplied by 2 times 10 to the 24 divided by 2 times 10 to the 7 squared, which gives me 0.3335. Which I will round to 0.334. Headed in this direction. So again, provided in that magnitude multiplied by the direction format. Okay, so if I'm going to do my net force then, or sorry, my net gravitational field, I have to take this field for pointing this way and this field pointing that way, and I have to add them like vectors. So I'm going to transcribe this down here so I have some room. My net gravitational field at that particular place will end up being the x coordinates added together, so that's negative 0.445 cos 19.5 plus 0.334 cos 40.5 comma the y coordinate 0.445 sine 19.5 plus 0.334 sine 40.5. Alright. So the advantage to doing it this way is that I didn't generate a whole bunch of decimals that I had to carry around with me. I could just plunk in that cos 19.5 and just leave it there. You might have noticed actually that I generated these angles by doing arc coses and arc sines. So if I had wanted to, I probably know the fraction for that so that I could put it in exactly and there wouldn't be any rounding at all. But that would be a little too much math even for here. So I'm just going to finish it off. I'm going to render this as decimals. So I will have to do negative 0.445 cosine 19.5 plus 0.334 cosine 40.5, and I get net negative 0.165. 655 if I round like this. In my y-coordinate, I have 0.445 sine 19.5 plus 0.334 sine 40.5. That gives me 0.1501. And we will end in green. Okay. So if I keep in mind that this net gravitational field is actually an acceleration, then any object I place here will start to accelerate at 0.1655 meters per second squared that way in the x direction, and 0.1501 meters per second squared in that direction. If you want it in components, then you're done. It's always good to put it back into that other format, which is the absolute acceleration and then an angle relative to your origin. So I'm going to get the actual size of my gravitational field here. Size of G net. Be the square root of this squared. I'm just using Pythagorean theorem. So 0.1655 squared plus 0.1501 squared is that thing, square root of my answer. Get 0.2234. And I need an angle if I'm going to use that. So this thing is going that way and then that way. 0.1655 and 0.1501. Okay. So to get this angle here, I'm going to use tan. So tan of that angle would be 0.1501 over 0.1655. So the angle is 0.1501 divided by 0.1655. And then arctan that. 42.2 degrees. Okay, now what I figured out then is that any object here is either going to accelerate that much in x and that much in y, or it's going to accelerate that much on an angle at that angle. Now 42.2 is an encouraging number. If you can take a look at the diagram and see where it would lie. Because my acceleration is going that way and up, it's over on this side of the triangle, and it's 42 degrees. If that's 19, then 42 is like this. So it's inside of this triangle that I've made, which is good, because I should have my net acceleration trying to pass between those two objects. All right, good. So I'm gonna, now that we've got our net accelerations and stuff, our net gravitational field, here it is. I'm going to erase this, and we're going to try a 3 mass problem. So I'll just clear off some space. So I'm going to try and determine the net gravitational field at this location, which is directly above that particular mass. So I left all the numbers for the triangle on there so that we didn't have to start from scratch. But basically, what I've got at this point is a field that's pointing in that direction. I have a field that's pointing in this direction, and I have a field that's pointing straight down in this direction. So I need my separations. I need that, and I need that. So I'm going to start by solving this particular piece here. So in that triangle, I have a hypotenuse that's 2 times 10 to the 7, and I have an angle of 40.5 degrees up here, and I need to know that, and I need to know this. And those two things happen to meet at a 90-degree angle. So I could use sine to find this side. So sine 40.5 would be the question mark over 2 times 10 to the 7. So pop that up here. Question mark is 2 times 10 to the 7 sine 40.5. 2 times 10 to the 7 times sine 40.5 gives me, goodness, 1.299 times 10 to the 7. 2, 3, 4, 5, 6. Yep. Smiley face then would be the same sort of setup, but it's adjacent, so I'd be using cosine instead. That'd be 2 times 10 to the 7 cos 40.5. So smiley face is 1.521 times 10 to the 7. And if this whole thing was 4 times 10 to the 7, and this little chunk is 1.521 times 10 to the 7, there's 4 times 10, then this piece here is 2.479 times 10 to the 7. Okay. So at this particular location, I have a field headed that way. I have a field headed this way. And I have a field headed to the right, like that. So for the blue one, let's use the yellow marker. I do a vector in green. Yeah. Gravitational field at that location would be 6.67 times 10 to the negative 11 multiplied by the mass of the object causing it, which is 2 times 10 to the 24, divided by the separation here, which was the smiley face, which is 1.521 times 10 to the 7. And I need to have r hat up here. This particular vector is pointing entirely horizontally with no vertical component. So the rules for this is that it has to be 1 unit long, and that's exactly how long it is. It has no vertical component, it's purely horizontal, and it's headed to the right, so positive 1 will do. So this vector then, 6.67 times 10 to the negative 11 multiplied by 2 times 10 to the 24. Keep forgetting to square this. Divided by 1.521 times 10 to the 7 squared. Well, I wrote the brackets, but not the squared. Equals 0.577. Well, let's keep 4 decimal places. 66, comma, 0. All right, the green force, or field, sorry. That would be 6.67 times 10 to the negative 11. The mass causing this gravitational field is 6 times 10 to the 24. The separation is this, which would be 2.479 times 10 to the 7 squared. And r hat, it is entirely horizontal, no vertical component, but it's headed to the left. So 6.67 times 10 to the negative 11 times 6 times 10 to the 24 divided by 2.479 times 10 to the 7 squared gives me negative 0.6512, comma 0. And finally, I have the pink vector here. So G would be 6.67 times 10 to the negative 11. The mass causing this gravitational field is 3 times 10 to the 24. And the separation here is the question mark, which is 1.299 times 10 to the 7. And my r hat, there is no horizontal component. It is entirely vertical, and that vertical component is headed down. So I'm going to use negative 6.67 times 10 to the negative 11 times 3 times 10 to the 24 divided by 1.299 times 10 to the 7 squared gives me 1.1858. All right. So just looking at what's happened here, it looks like this is the dominant term, this pink one from this particular mass. So we try and figure out why that is. This distance was 1.299 and this was 2.4. So this is basically twice the distance that this is. And in your calculations, the r gets squared and the driving mass does not. So despite the fact that this thing is twice as heavy as this is, the fact that it is also twice as far away makes its gravitational field half as strong. Let's think about that. This one over here, the distance, this was 1.29, this was 1.52, so this one's a little bit further away, and it's considerably less massive. So the field here is less than the one that's here. Okay, good. So in order to get my net gravitational field, I'm going to have to add all of these up. So 0.5766 plus negative 0.6512 gives me negative 0.0746, and the only vertical component I have is negative 1.858. Okay, so that is the net gravitational field in component form. To put it back into full vector, or I don't know what you want to call this exactly, I'm going to use Pythagorean theorem. So 0.0746 squared plus 1.858 squared and then square root that answer gives me 1.8595 meters per second squared. And the angle, let's see, if it's headed left and down, that's the angle I'm after, and I have 0.0746 here and 1.858 here. So I'm going to have to do arctan. 1.858 divided by 0.0746 equals, and then arctan that answer gives me 87.7 degrees. From horizontal. Alright, lovely. So this object, an object placed there, it won't head directly towards this mass. It will head off at an angle of 87.7 degrees, which is going to take it sort of in this direction, like so. Really close to this guy, but not quite. Alright, now having done those calculations, having done this one, as soon as you move from this location to this location, all of your distances have changed. So as soon as your distances have changed, all of these force components have changed, and so your net acceleration will be different. If you just think about it, at this place I'm a little bit closer to that, not much closer, not a little bit further away from that, but I'm a lot closer to this one. So my vector, which used to point that way, might start to point this way a little bit more, which is going to bring me to here, which is going to make these less effective. So I might end up getting stuck sort of orbiting this, or I might end up plummeting onto the surface. I'm not sure, but I would have to recalculate this net gravitational field every time I moved, which is irritating. It would be better if I could leave these with a variable in it, or a set of x-y coordinates. And so when you get to like university doing engineering or physics, that's how you would handle this. Instead of doing net field at a particular point, you try to do it everywhere, but that would be a bit much for us. So in the practice problems, it does ask you to put your answers in component form. It asks you to put them into combined form. It asks you to put them in magnitude g hat form. That's this kind of thing. It asks you to do a question where you find a place dead center between two objects. So that's just two components. You can work that out. It does ask you to take a third location and remove it, and then do the net force from those two. And then it asks you, just for practice, to put this one back, scrub that one, and repeat the calculation at this point. Put that one back, scrub this one, find the net field at that place. So it's lots of work. I will give you some time.